We're going to look at rational functions, and in particular we're going to look at horizontal and oblique asymptotes. I'm going to explain what those are, and then I'm going to show you how to find them. So here we have two graphs of rational functions, and they have these kind of funny graphs, and we've already seen something called vertical asymptotes. So like in the first graph, I have these vertical lines here that the graph doesn't touch, and those are called vertical asymptotes, and we saw how to find those from the denominator. But now we also have these new things. For example, in this one we have a horizontal line that goes across here that the graph does not touch. This horizontal line is what we call a horizontal asymptote. And technically you could have a graph that looks like this, where you still have a horizontal asymptote that you do cross. It crosses once. But what's going on is your behavior to the left and to the right approaches this horizontal line. And that's really the defining characteristic of a horizontal asymptote. Most of the time we say that it's a horizontal line the graph doesn't touch. Okay, now the other type of asymptote we can look at here, so in the second graph, here I still have a vertical asymptote right through here. But I also now have a asymptote that's not horizontal, but it comes in kind of at a diagonal, and that's what we call an oblique asymptote. Your textbook may say slant asymptote as well, but these are the same topic. Alright, now I'm going to show you how to find these. It's really not very difficult, and I hope it makes sense. Okay, so to find horizontal and oblique asymptotes, first we need to let our rational function, we're going to call this f of x, be equal to p of x over q of x, and we say that because rational functions are polynomials over polynomials. And what we really need here is that we need to know a little information about these two polynomials. So let's say p of x starts out with a x to the n plus some stuff, and we don't really care what the rest of it is, to be honest. And in the denominator we have, let's say b x to the m plus some stuff like that. And we don't really care what happens past those first two terms in the numerator and the denominator. Those are going to determine everything about this. Okay, so let me explain this with a chart. First of all, if n is less than m, that means the degree of your numerator is smaller than the degree of your denominator. You're going to have a horizontal asymptote with equation y equals 0, right? Y equals a constant, it's a horizontal line. So if the denominator has a higher degree, your horizontal asymptote is going to be at y equals 0. If the two degrees are equal, if n equals m, you're going to have a horizontal asymptote at y equals a over b. A over b, remember, being the leading coefficients of the numerator and the denominator. And if the numerator has a higher degree, you have no horizontal asymptote. And it's that simple. Okay, now there is one extra thing. Where do slant asymptotes or oblique asymptotes come into play? If your numerator is greater, but it's only greater by 1, so n equals m plus 1, then that's when you have your oblique asymptote. And the way you find your oblique asymptote is through division. And I'll do examples to cover all of these cases. Now, one thing I do want to point out, this isn't just some made-up thing. The reason it works the way it does is because imagine with this polynomial, we're talking about, again, in behavior, meaning when x goes out towards infinity. So in other words, when x gets really, really large, either in the positive or the negative direction. The driving force of the numerator and the denominator comes from this first term. Because the x values are so large, the rest of it doesn't really matter. For example, if I said, hey, here's a check for $4,035,000, you don't even hear the 35 cents. In fact, why don't you just keep the 35 cents? Who cares about that? I want the $4 billion, right? And that's the same thing that's going on with these polynomials. When you plug in these large values of x, that x to the n, x to the m, those are the dominating terms. Everything else doesn't really affect what's going on. So if you have n is less than m, for example, that means that the denominator is growing at an exponentially higher rate than the numerator. So the numerator cannot keep up, which means this number, this a over b term here, is getting smaller and smaller and smaller. It's approaching 0, and that's why we get y equals 0. If they're growing at the same pace, if n equals m, then as x gets to infinity, it just levels out to this ratio, y equals a over b. And if the numerator is growing faster than the denominator, it's not going to have an asymptote because the numerator is dominating what's going on. It's going to blow up to infinity. Okay, so that may make sense to you. That's the explanation of why we get these. Now let me show you some examples on how to work these, and I think they'll go by pretty quickly. Alright, so here we have in part A, so we're trying to find horizontal and oblique asymptotes. For part A, I have f of x equals 3x to the fourth plus 11x squared minus 15 over 21x cubed plus 2. Man, now if I had to factor this, that would be a really hard question. But just finding asymptotes is actually not very hard, the horizontal and oblique asymptotes here. Because what I want to do is keep up with, alright, now remember, we said we want to think about f of x being something like this. Ax to the n over bx to the m plus, we don't really care what's after that, okay? So in this case, my n is 4 and my m is 3, which tells me that n is bigger than m, and that tells me that the numerator is growing faster than the denominator. So if I plug in, for example, a billion to the fourth power, it's way bigger than a billion cubed. So this means I have no horizontal asymptote. Now for part B, we have 12x to the fifth minus 11 over 4x to the fifth plus 3x to the fourth minus 2x squared plus 55. Again, thankfully we're not factoring here, right? So my numerator has degree 5, n is 5, and my denominator has degree 5 as well. So that means that they're equal, and so that means I do have a horizontal asymptote, and it is y equals, let's see, if they have the same degree, we said that would be the ratio of the two leading coefficients. So that's going to be 12 over 4, or we might want to say that we have a horizontal asymptote at y equals 3. Alright, now for part C, we have h of x equals x cubed plus x squared plus 2x plus 2 over x squared plus 9. Okay, so this time that means n is 3 and m is 2. That means then that n is greater than m, which tells me again the denominator is growing faster than the numerator, so I have no horizontal asymptote here. But in this particular case, notice that the numerator has degree 1 larger than the denominator. So I don't have a horizontal asymptote, but I do have a slant asymptote. And the way I find that is through division. So let's do that. Okay, so I'm going to set this up as x squared plus 9 going into x cubed plus x squared plus 2x plus 2, like that. Okay, and remember the way polynomial division works is I got to think what times x squared gives me x cubed. So x squared times x gives me x cubed. And I have a video going over polynomial division if you need it, okay? Now you distribute the x and you get x cubed plus 9x squared. And from there, you subtract. So I'm going to subtract everything. And so I have x cubed minus x cubed is 0. And x cubed minus 9x squared, x squared minus 9x squared is negative 8x squared. And I bring down my plus 2x. And I go again. X squared times what gives me negative 8x squared? How about negative 8? And then I distribute the negative 8 across to get negative 8x squared. There's no x term, so it's plus 0x. And then negative 9 times 8, 72. Okay, so now I'm subtracting. So subtract, subtract, and subtract. So I get 0x squared, 2x, and I need to bring down my 2. So that's going to be 2 plus a 72, get 74. And this will be my remainder. Alright, that's the remainder. But my asymptote comes from right here, the quotient. So my slant asymptote in this example is y equals x minus 8. Now you do have to do some polynomial division, but you know what? It's always a pretty quick polynomial division example because your quotient will always be first degree, right? Because it's a linear expression, because it's an asymptote. It's got to be a straight line. Okay, so horizontal and slant asymptotes are not very difficult. You can memorize the table if you want to, or you could try to think how quickly the numerator and the denominator are growing. If the numerator is outpacing the denominator, there's not going to be an asymptote. If they're growing at the same pace, it'll be the ratio of the two leading coefficients. If the denominator is growing faster, your asymptote is y equals 0. We've shown some examples of this. I hope they make sense. There's really no curveballs of this. If you have any questions, I'd be glad to help, and thank you for watching.